Good morning everyone, I am Mr. Ish. Thank you for joining me for this video. The easiest way to understand limits titles our video today, and it should be a relatively easy and comfortable video because it will tend to be more or less conceptual and less technical in nature. There have been a variety of limit videos already released on this channel, so by now we are comfortable with determining limits, but let's look at limits in a more layman's perspective. The easiest way to understand limits, in my opinion, is by means of graphs. And you just understand the graph and you read off the limit from a graph. But what exactly is a limit? If someone were to ask you in a very simple manner what exactly is a limit, you could define a limit using non-technical terms in the following way. A limit is basically a means of understanding how a certain function behaves when it is affected by a given stimulus. Think about it. From a practical sense, in the scientific disciplines, no matter what the discipline may be, at the end of the day, all functions are representing some sort of models, right? Isn't that the whole purpose of functions? Because they represent a given model which will probably represent some real life event. And if a function which is representative of that model is studying a behavior of whatever physical, biological or chemical phenomenon, and you want to understand how that phenomenon is affected by the impact of a stimulus, that's exactly what a limit is. Limit is basically studying how a function will behave or react. More so react to a given event. And what's that event going to be representative of? And what is the reaction going to be representative of? It's exactly what you might be thinking. The event will be more like an x-axis stimulus or an x-axis variable, and the reaction or the behavior will be represented by the y-axis. And and another way to look at all of this is the event or the x-axis values represent your domains, right? How a function behaves and how you read your model off to determine what that behavior or reaction is. You're looking here at the range. We know limits are written in the following way. Limit as x approaches a given value, we'll call that a. What happens with the function is what we have to determine. And the most easiest way to understand how limits are or what limits are is to look at things in this perspective. You have a given function which represents a model. You're trying to determine how a function reacts or behaves when a given event occurs or a given stimulus is affected or impacted upon that function. And that function is most likely going to have a practical value in that it represents a given phenomenon or a practical phenomenon, be it biological, chemical, or physical, whatever it might be. And you're trying to determine this as a result of your functional model and how it reacts to a given stimulus. You can represent it in this way. So let's look at some ways in how we can put this into perspective with regards to the functions that we are familiar with. This serves here as a template for what a function looks like in terms of terminology. If you were to graph a given function, it could be anything. You're looking at x approaching a. Let's represent this a over here. You can have these x-axis values here. These are my y-axis values. X can approach a from the right, or x can approach a from the left. When x is approaching a from the right, you can call it this. These are x values approaching a from the right. When x is approaching, or the x values are approaching a from the left, these would be this. From the left side, you're approaching a. The best way to understand limits is to be able to read a limit or a function upon a graph. As x-axis values are approaching a from the right or the left, you're basically looking at how the function reacts. So you're looking here at domain values. The domain values here are representing the stimulus or the impact of your model upon that function, or the impact of your or stimuli upon that function or the model that it is. And then you read across right here to your y-axis value, which represents the range. And this right here at this value over here is what we end up putting here as a value of our function. That how the limit behaved or how the function behaved as x approached a given value. And that right here, it represents in a very easy manner what a limit is, what it is. That's what we're looking at. You're looking at the behavior of a function as something happens to that function, and that something happening to the function is represented here by the x-axis values. How your function actually behaves or reacts is then given here by the y-axis value. Let's look at just a practical example over here. It can be purely hypothetical, but again it'll stress the point that the easiest way to understand limits is by learning how to read graphs. You have a graph over here. On the x-axis you have an independent variable, time. Time is usually an independent variable because it is not affected by anything, whereas it impacts other variables. Number of population of whatever species you're talking about, which would be your y-axis values, would be a dependent variable, because with time the population counts can change, right? So this is affected by time and other events that might come in, but definitely time is an independent variable. The population count of whatever species would be a dependent variable. At a given point, and you know this right here is the origin 0, you have no population, but at this point over here it could represent whatever, we'll just call it 1, and this time can be in years or it could be in decades. At a time of 1, a certain number of species migrates onto an island, so you have now a certain given population over here, and we can, let's say 100. Over time this population, it expands, it reproduces at a very fast rate, such that at the highest level you probably have a count of 1,000. The highest population count 1,000, but as resources begin to run out, the population dwindles until it reaches a stable value, and we can say right here this was probably 100 years, and this right here onwards, as the population is plateaued, we can say this can be like 200 years, and the population count here, the stable population count, probably is represented here by, let's say, 250. If you were to look at this, it would very well mimic a biological phenomenon that resources are limited, and therefore the limit of those resources affects the population. Initially populations increase, but then they eventually reach a plateau. Limit as x approaching a f of x. If we are looking at this definition over here of a function, how can we use that to help understand what a limit is in terms of a graphic interpretation? Well, we can. If supposedly the question was limit as x approaches 1, how does your function behave? And again, the function is represented by this model. This model represents exactly what you're seeing, the population count over a period of time. Limit as x approaches 1, all you have to do basically, if you are able to have a graph and avoid the calculations, you're just looking at x-axis as they approach 1 from the right or from the left. Remember, if the x is approaching the a value, these are a values here from the right and the left, and they lead to the same result, then the right side and the left side limits are exactly the same, then the limit actually exists. If the right side and the left side limits are not the same, then you know the limit does not exist. Therefore, you cannot develop an answer for that given point as x is approaching a. But in this case, as x is approaching a from the right and x values are approaching a from the left, you just have to read across and you look across here. So limit as x approaches 1, your function approaches 100. What does that mean? That as you're looking at the model at the year 1, you have a population which is represented by 100. When we look over here, as x approaches 100, limit as x approaches 100, your function will do what? It'll approach a 1000, because that tells you exactly how the function is behaving at that point. At a time of 100 years, the population is at its peak, and you're looking across and you're reading the range value, which is your y-axis value, and you know 1000, and then limit as x approaches 200. These a's are representing years. 200 years, you're looking across on your function, reading across, you know your function approaches 250, but it's more than that. You don't even have to worry about these specific points. You can look at any point over here and do exactly that. Limit as x approaches whatever this value is, you read across and you get your function as it behaves at that point. Look over here, read across, and you'll see exactly how your function is behaving. So the best way to understand limits is by means of graphs, and the best way to understand what a limit is exactly how you're thinking about it, that at a given time or a given event, there's a certain x-axis value which represents a independent variable. Something is impacting that, and then you're seeing how the function behaves or reacts to that, and you have to basically look across your function and read the y-axis value, and that y-axis value will give you exactly how your function behaved or reacted at that given point in time. Because this is relatively a conceptual video, and we're just trying to prove the point that the best way to understand limits is by means of graphic interpretation. It doesn't have to be a long video by any means. We're going to look at these two examples and that'll be it for this video, because I just want you to have the take-home message that if you're able to get your hands on a graphing software, or if you can learn how to graph, you can very simplify your limit determinations, and you can always use your limit determinations based on these graphic interpretations as a means to verify that your calculated answers are indeed true, or close to being true. We have here a graph of secant hx, and down here we have a graph of a hyperbola 1 over x. If you look here at the first graph, you know the graph has a domain minus infinity to infinity. It has a range from 0 up to 1. So this right here represents a good graph for secant hx, hyperbolic secant hx. If supposedly the question was limit as x approaches 0, what does the function approach? And by function I mean this hyperbolic secant. Where does it approach? You just read your graph. And you always want to test the right side and the left side limits, because if the right side and the left side limits are the same, you will have a limit that exists. But in those cases where the right and the left side limits are not the same because the function is discontinuous, look here at an example here and here. If you look limit as x approaches 0, because this right here represents my 0 in terms of the x-axis values, your function will not exist in terms of having a limit, because the right side limit and the left side limits are different. Here the right side limit coming from the right will have a value of a positive y. The left side limit coming from the left will have a value of minus y. Therefore the right side and the left side limits are not the same. The limit does not exist. But in these instances, in this first example where I'm looking at, the right side and the left side limits will exist. Just read your graph. As x-axis values are approaching the right up to 0 and from the left up to 0, your function, and where does it go up to? Look at the y-axis values. It goes up to 1. So the answer here would be 1. All you have to do is read the graph. At x-axis value of 0, your function approaches 1. How about this? Limit as x approaches infinity. As x approaches infinity, you can look over here. As x-axis values are going towards infinity, where is your function approaching? You can do right side and left side approximations by testing values, or you can just look at your graph. Your graph is going eventually, your curve is going eventually down towards 0, never getting right to 0 but up to 0, and you can read your graph and you know your function will approach 0 as x-axis values approach infinity. If you're going towards a minus infinity, limit as x approaches minus infinity, again your function is, the curve is dipping down towards the x-axis but never getting close enough that it is becoming the x-axis, but it's trying to get close to it, and again your function approaches 0. And you can see graphic interpretation is very easy. The only other way you could do this would be having to test your values, or you could do with the functional definitions. And let me show you just example over here, f of x as x approaches infinity. How else you might have had to do it if you didn't have the graph available? You'd have to do things the long way. We're looking at the secant hx, which is the same thing as 1 over cosine hx, which is the same thing as 1 over e to the x plus e to the minus x over 2, which is the same thing as flip over this e to the x plus e to the minus x. Now you're plugging in limit as x approaches infinity. In places of these x's, you're having 2 over e to the infinity plus 1 over e to the infinity. You might have seen this all in the hyperbolic limit video. This zeroes out. As x values approach infinity, this zeroes out. You're essentially having 2 by an exceedingly large number that it again zeroes out. As you can see, your graph dips towards the x-axis, never becoming the x-axis, but is eventually trying to reach it. So you can say limit as x approaches infinity for this function, your value is 0. But see, the graphic way of determining the limit is so easy. The non-graphic way requires work. Let's look here lastly at this hyperbolic function. We have this curve and we have this curve right over here, 1 over x. If someone were to say limit as x approaches 0, what does your function approach? Well, when x approaches 0, you're looking at these values here from the right, and you're looking at these values here from the left on your curve. When you're looking at x approaching 0 from the right, I'm going to put a pause there. Your function moves up steeply up towards positive infinity. You can see it, trace the values. It's going to go up to positive infinity. As x approaches 0, but from the left, the function dips down towards minus infinity. See, here it's going up towards positive infinity, here it's going minus infinity. So here in this instance, it's going to minus infinity. So what's your answer here? If someone were to ask you limit of f of x as x approaches 0, your answer is the limit does not exist. Why does it not exist? Because the right side and the left side limits are different. They're not the same. Because the answers are not the same, the limits are not the same, it does not exist. D and E does not exist. How about looking at the same curve and we look at this part, limit as x approaches infinity. As these x-axis values are approaching infinity, where is your function going toward? It's going to keep going and getting close and closer to this x-axis line, and you know your function is going to approach 0. And you can think about it in this way, your function is 1 over x, you're essentially doing 1 over infinity, which is going to zero out, hence it's 0. What about limit as x approaches minus infinity? Then you're looking at these values here on the curve going towards minus infinity. And again, your curve is coming close to this x-axis, and again you can say f of x is equal to 0, because you're going to do 1 over minus infinity, which is still a 0. It doesn't matter if it's a positive infinity or minus infinity. 1 divided by such a large number is always going to 0 out. So here your function is going to approach 0 as x approaches minus infinity. But what if you were to look at any value in between, right about here, right here? And let's call this 5. What happens to your limit, your function? What happens to your function as x approaches 5? What will your function approach? This is easy. In this case, just look at your graph. At an x-axis or domain value of 5, you look upward and you look across on your graph, and you know your function is going to approach 1 over 5. Why? Because your graph is represented by 1 over x. You can simply plug this 5 over here. But if you didn't want to plug 5 over there, and you wanted to rely on an approximated result, you can bring out your calculator and you can test right side and left side values. A good right side value to 5, a value close to 5 but on the right side would be 5.001. A good left side value would be 4.999. And then you plug these into your function 1 over x. This way you're not saying that I'm directly plugging the a value into the function, you're doing an approximation. If you do 1 divided by 5.001, you get 0.1999. There are a bunch of other numbers, but I won't write them. I'll put a 6. If you test a 4.9, remember this is a value coming towards a 5 but from the left. See, 4.99 is the value left of 5, 5.001 is the value right of 5. Then let's run 4.99. 1 divided by 4.999, I get 0.20004, and we know exactly 1 over 5 is just 0.2. But look at these, as you add more zeros here for this right side value, or as you add more 9s, these values are going to come close to this value right here, 0.2 or 1 over 5. So you can clearly say limit as x approaches 5, this function will approach 1 over 5. And likewise for any of these negative numbers here, if I had a minus 10 over here and I'm seeing how my function will behave as I plug in a minus 10, I can read across. In this instance, limit as x approaches minus 10, my function will approach, and you know it, minus 1 over 10. You just have to read across. Again, it'll be a minus 1 over 10, which is a minus 0.1. Proving the point again that graphic interpretation is the easiest way to understand limits, and it is by no means cheating, because you're using the graphing tool to understand how to read a graph to determine limits, because that in essence will teach you why you are learning limits and how a function is behaving at a given point of time when something happens to it. These things happening to it are determined here by your x-axis values, which are your independent variables, and how your function behaves or reacts is determined by you reading your function graphs based on the y-axis values, because that tells you what happened to the function at that given point in time, and that's your reaction of that function. That'll be pretty much it for this video. I hope you understand this video and you appreciate the fact that graphing, learning to graph, and the interpretation of graphs is basically the best way, especially for starters, for people starting calculus, to understand the concept of limit. Everything else then will stem from there in a logical manner. Thank you for watching. Have a nice day.